So in 6.1, we first introduced the standard normal distribution, or the Z distribution. We briefly mentioned normal distributions in general. So remember, a normal distribution is a continuous probability distribution. That means the random variable that's normally distributed, we usually call it X, can take on decimal values. It's going to have a bell shape to its density function, a bell shape. And in the center of the distribution, you're going to have what's called the mean. It's going to be the mean. We call that mu. And this curve, this red curve, that's called the density function. It shows you how things are distributed. The PDF, that's the probability density function, it has a formula. The function is f of x equals 1 over sigma, square root of 2 pi. So pi is just the number about 3.14. Sigma is the standard deviation right here. Standard deviation. So these are just all numbers, right? Sigma is just a number. This is going to be multiplied by e to the negative 1/2 x minus mu over sigma squared. Okay, mu here is just the mean. So sigma is going to be a number, that's going to be your standard deviation. Mu is going to be a number, that's going to be your mean. X is a variable. Pi is a number, that's 3.14, and e is a special number, that's the exponential growth number. It's about 2.1718. So that's what happens when you graph that function. You get that red bell-shaped curve. It's called a normal distribution. So some things about the normal distribution: the standard deviation and the mean, you can alter those. So if I keep the mean the same, so let me draw a picture. This is my normal distribution for my variable x. Let's say I keep the mean the same. I don't change that number. But I make the standard deviation really big. So big standard deviation. So what happens when the standard deviation is big? What that does, that kind of flattens out your curve. So rather than having a really tall curve, it's going to make your curve a little flatter. It's going to have fat tails. So what happens when the sigma is big, when the standard deviation is big? So number one, the curve gets flatter. And number two, the tails get fatter. That's what happens to the normal distribution when I have a big standard deviation. Okay, what happens when I have a really small standard deviation? That's the question. Small standard deviation. So when I have a small standard deviation, let me go back and draw my distribution. Oops, the wrong color. Here's my random variable x. Let's keep the mean still the same. Let's not change that. Still mu. So when I have a really small standard deviation, that's going to make my curve get really tall, and my tails are going to get really skinny. So number one, the curve gets taller. And number two, the tails get skinny. If you think about it, if you have a small standard deviation, that means the data is not very spread out, right? The data is closer together. So most of your data is going to be clustered here around the mean. If I had a big standard deviation, let's go back to the previous picture, that means my data is going to be more spread out. So there's going to be a lot of data out here on the tail. So that's why the tails are getting a lot fatter out here, right? Because the data has to spread out. It's not going to be all clustered in the center. So the center is not going to be really tall. It's not going to be really tall in the center. It spreads out in the tails. So it gets fat in the tails. That's kind of the idea. Okay. So we looked at the z distribution, the standard normal distribution in 6.1. So we're actually going to use the z distribution. We don't want to forget that. Why do we want to use the z distribution? Because we know how to find probabilities with the z distribution. So we want to have some formula for converting normal distribution values these are called your x values, your normal distribution values, to z-scores. It turns out that the z-score is your normal distribution value, x, minus the mean of the normal distribution, divided by the standard deviation of the normal distribution. So again, z is going to be the z-score. That's your standard normal random variable score. X is going to be your normal distribution value. Mu is the mean of the normal distribution, and sigma is the standard deviation of the normal distribution. So that's a useful formula. So it turns out that a lot of things in nature often tend to be approximately normal. So for example, like weight, height, IQ is a really famous example that's been well studied, well documented. The research shows that IQs are pretty normally distributed. They have a bell-shaped curve to them. So we want to work some exercise